All right. Hello, everyone. I'm Han from the Ethereum Foundation. I'm part of the stateless consensus team. So we basically work on things regarding state. So the problems that we solve are mainly like state growth and basically how would the state look like in the next 10 years or 100 years even after we ship zkEVM in the future. So today, the talk is about understanding more about Ethereum state, because previously we don't really understand Ethereum state as a whole. Like we don't know what are the state access patterns. We didn't really know what to expect from a state perspective. So hopefully this talk will give you a comprehensive overview on the data that we gathered from state. So let's get started. So, well, Ethereum state, when we talk about Ethereum state, is basically these three things: accounts, storage slots, and contract codes. So when someone talks to you about Ethereum state, it's these three things. And this state, all of this state are represented in a Merkle-Parisha trie. So it's actually two-tiered. So you have the account trie where all the leaves are the accounts. Then for each account, you may or may not have a storage trie. And in the leaves of the storage trie will be 32 bytes value. So that will be your contract storage. So this is the structure that we have currently. So one problem that the core dev community or in general the community has been discussing is on the problem of state growth. So the idea of state growth is that the number of accounts on Ethereum can actually grow kind of infinitely, not really infinitely because it's 2 to the power of 256, but it's large enough that it's practically infinite. And the same goes to the number of storage slots that a single account can store. It's also 2 to the power of 256. So in other words, the state will just grow, meaning the state size will become larger, or meaning the number of storage slots will just keep increasing, the number of accounts will also keep increasing. This is one example that we have. So this is 281 gigabytes. So this data was extracted, I think, a few days ago. This is extracted from a Go Ethereum node, and this is only on the trie size. So if you compare between different execution clients, you can actually see different numbers, but more or less they are the same. And this is also the lower bound because internally in execution clients, they have additional data or additional indices to actually make certain operations faster. So it's around 300 to 400 gigabytes for now. So now let's explore a little bit from the perspective of data in each of the state type, and let's start with accounts. So accounts, we have two types. One type is EOAs, another type is contract accounts. So we're gonna look at EOAs for now. So we are looking at in terms of activity span. So the definition of activity span here means the block difference between the first and last state access. In terms of accounts, then what is state access? It means that if some operations on-chain touches a certain state, or means it has to load the state from the database, then that's state access. So it doesn't matter if it's read or write. So in terms of like operations, that means you are sending or receiving ETH. That's for accounts, or in terms of storage slots, that would be sload, the opcode sload or store. So for EOA activity span, so we can actually see that 80% of the EOAs are active for less than a year, which kind of, this is not surprising to me because like me personally, like when was the last time that I actually interacted with my EOAs? And let's say I have a lot of EOAs, and some of them I don't really interact with very often, some of them I do. So I think it's the same with, I guess, most of the people here. So, and some even have zero activity span, meaning that a zero activity span means that this account was only seen for one block, in a single block, and that's all, right? So that's, this is not a lot, but if you look at contract, it's actually a lot. So 55% of all contracts ever deployed are deployed once in a single block and never touch again. No calls, no state access, nothing. So, I think it's too early to say that these are garbage contracts. Maybe they are spams. That's my speculation, but it could be. Or they could also be off-chain reads, but how much proportion of that, we don't know. But yeah, in general, accounts are not very active for very long, right? But on Ethereum, we do make the promise that we want to have all of the state to be permanent on-chain forever. But on a practical point of view, maybe we wouldn't want that, or we wouldn't want that completely, so that we can actually scale safer, which I'll touch on later on. So another thing, we can also look at contracts by deployer, meaning who actually deploy all these contracts, right? So we have the data here shows 50 million. That was, I think, the number from 2 million blocks ago. Now we actually have like 60 to 7 million contracts. So here we can actually see that 0.009% of deployers actually created 57% of all contracts, which is why my suspicion is that there is someone spamming, or there's someone that's creating these contracts without any reasons. So, and they are not useful. I mean, I cannot justify or I cannot prove it, but that's my speculation. Then, from another perspective, we can also categorize contracts with storage or without storage. Meaning, with storage means that it contains at least one storage slot, and without storage means no storage slot at all. So the proportion is quite half. I mean, with storage is like 46%, and without storage is like 54%. So that's pretty close. But one interesting thing is that we realize contracts without storage are 30 times more active than contracts with storage, which means, again, we have to dig into what these contracts are, what are they used for, but I'm guessing is that there are some utility contracts that are deployed that have no storage. Only the code is useful, and they tend to be called more often than the ones with storage. But yeah, that's one interesting data point. Right, next, bytecode or code, or contract codes, right? So that's one thing that we can look at as well. So we have 50 million now. I mean, now it's like 60 to 70 million contracts. But if you look at that in terms of unique bytecodes, here it's only 1.6 million. The current number is about 2.1 million, which is still not a lot compared to the number of contracts that we have. So one common misconception that people have is that, oh, we have 60 million contracts on Ethereum. There must be a lot of unique applications. Not really, because the unique application actually derives from the bytecode implementation. So if you look at the unique bytecodes, it's only like 2. I mean, here is 1.6. The real number is 2 million. So it's actually not a lot, and some bytecode implementation can also only have like a slight difference. So the actual unique implementation is actually even lower. But in general, like 97% of the contracts reuse existing bytecodes, which is something that we can actually optimize in protocol, which I'll talk about later. Then we look at the distribution of the contracts in terms of code size. So this is how the distribution look like. So most of the bytecodes, unique bytecodes, are actually under 5 kilobytes. So yeah, so with most of the contracts being the tiny contracts, which is, a tiny bytecodes, which is less than 1 kilobyte. That makes sense because it's cheaper to deploy small contracts with smaller size, right? Whereas if you look at like very large contracts, it's more expensive. It also makes sense from an application developer point of view. And for the contracts that actually use up all of the like 24 kilobyte max contract size, actually very, very little. So there are some like discussions on like increasing contract code size. Yes, there is some demand for it, but is the demand really represent like all of the application developers? Maybe not, because internally, not internally, but like we have talked to some application developers, and they say that they have already adopted to the philosophy of like modularizing their whole application. That it's not. Having higher contract size is good, definitely, but by having modularity, maybe it's not that important. But this is one perspective, but it's not 100% true. So for everyone, so yeah. Then we look at bytecode access patterns. So this is one interesting point when it comes to also optimization and also for ZK EVM. So you have a bytecode, right? You can think of it as a series of arrays. Like an array. So what's the proportion of the bytes that are actually used, right? Or to put it simply, like how many functions do you actually use typically on a contract? So It's actually very little. It's like on average, it's like 23% of the bytecode is used during during a block execution, right? On average. So the problem with this is that when internally, when you are calling a contract or when you are accessing a contract, you actually have to load all of the entire contract bytecode, which is inefficient because you know that around like 20% is only actually used. So later on, we'll introduce the concept of code chunking, and that will hopefully help solve the problem. And it's also a bottleneck in ZK EVM because now ZK EVM has to take up the entire bytecode as like a input to their proof system. But and that's one of the attack vectors. So yeah, we have to solve this problem in the future anyways. Lastly, let's look at storage slots, right? And first, let's look at activity span. So yeah, this is even worse than contracts. 63% of the storage slots have zero activity span, meaning they are written once and never touched again in a single block. And if you look at the entire thing, basically they are inactive for, they are active for at most 1 year. Yeah, so that's why, again, like I think that there's just a lot of spams, a lot of like garbage data on chain that is not really helpful. So this is similar to the accounts, but I think this is worse. Then again, we look at the perspective on concentration. So the top 1,000 contracts actually hold 51% of all storage. From a healthy perspective, I think that makes sense because, I mean, when I ask you about what are the applications that you actually use on Ethereum, you would say the few names, like what are the contracts that you actually interact with, and because they have so many users, they would naturally grow their state more. But from a malicious point of view, there are also some actors that have inefficient storage design and is bloating the state purposely. Right? I won't say the name. If you know, you will know. But yeah, that's one power law distribution scenario. Yeah. So I would describe what I've presented as like a preliminary, like an early data analysis on Ethereum state. I think there are a lot of things that we are still trying to understand in order to help us make certain protocol decisions. So the next part is to explore what are the things that we are actually looking at to turn this turn this data into protocol decisions. Yeah. So one thing that we're looking at is the state expiry. I mean, this is not new. It started at like a blockchain rent idea 10 years ago. Then I think in 2021, Vitalik wrote some papers, some articles on state expiry, and then people realized that it's too complicated, it's too hard. Then the research kind of died down, and then now I'm trying to revive this area of research. But the benefit is pretty clear, right? We know that a lot of the state is garbage. 80% of the state is garbage, right? The 2080 Pareto principle. So the benefits are clear. We have done the benchmark. We remove 80% of the state, and we know that there's a benefit in terms of like EL clients. They get better performance. Their DB performance is much more stable because it's not just about removing the garbage state, but it's also having an upper bound on the active state, right? So because if you know that there's an upper bound, you know what's the worst case. You know what's the worst case. That means you know what to expect over the long term, right? So even if you scale Ethereum up until 1 gigagas per second, you know what's the worst case that you can get in terms of state. But right now it's not the case because the state will just keep growing. And even with the repricing, we have to like adjust the pricing to become more expensive because the state size gets larger. So that's not really good for everyone in the community. Yeah, so we would ideally want to remove the garbage one way or another. So I think I should have talked about this. So the concept of state expiry is is to remove the garbage, but it's not remove it forever. It's to remove it temporarily. So while providing a way for users to revive it later on. So it usually consists of 3 things. So you need a way on identifying like what's garbage and what's not. Okay, I'll stop using the word garbage. Let's use active and inactive. Differentiating between what's active and inactive state. So usually you would need to have like in-protocol metadata to the state. Then the second part of the expiry is to wait a way for to know what's expired or not. So for example, if a transaction touches an expired state, then it should revert, regardless of whether you really have the data or not. Then the third part is for users to resurrect the state. So typically done through a transaction with a proof. So yeah, again, the benefits are clear, but the biggest problem is the user experience. First, so how would users, let's say we do this, then when we expire some of the state, then how would users actually revive it, right? Yes, they can use centralized RPC providers, but that's not really the long-term solution that we want. So ideally, we need to have a reliable, censorship-resistant way of providing the users the state that they need in order to resurrect it on-chain. Previously, one good solution is the Portal network, or more specifically, the Portal state network, but that's not really coming along right now. So we need to have an alternative before we can do this, right? So that's one main blocker. So if we decompose the problem of state growth, it's actually really just two things. It's state growth, increasing state size will cause two problems: increasing the state access cost, meaning the DB performance, worsening the DB performance, and also increasing the state holding cost, meaning the state size now from, for example, 400 gigs, it becomes like 600 gigs. So I would argue that the latter problem is not really that important. I mean, for now. I mean, it's easier to solve because you can just switch you can upgrade your disk, and the state is not growing as fast as history or chain history. So the more important problem that we have to solve is the performance of the database. And that's why you can see like a lot of the chains are doing a lot of their customized, database that's much more performant than what we have or what the current EL clients are using right now. And yeah, that's the reason. So from that perspective, we can one solution that we can do is to do hot cold storage separation. So the meaning of hot cold storage separation means that hot means active, cold means inactive. So in some ways, state expiry is like a form of hot cold storage separation where the protocol only keeps the active state, and then for the cold storage, it delegates the responsibility to the users to actually revive it later on. So there are many variants. So one variant that I'd like to present you is the very recent EIP. It's called EIP 8188, that we only target state writes. So basically, just to summarize, you have two tiers. One is active tier, another one is dormant tier. So if a state hasn't been mutated for a long time, then it would demote it to like a dormant tier. And if it wants to become like an active tier, then you have to pay like a higher cost. So having these two tier separation in terms of storage allows the execution clients to actually optimize their storage layout, because again, you are decoupling you are removing the garbage state, potentially garbage state from the active state. So the active state is again bounded. So that helps with the performance, right? But it doesn't help with state holding costs, because the state size will still grow. So, but there are certain interesting optimizations that can do, like optimizing the dormant state layout. But yeah, there's a lot of design choices. The next thing is to introduce new types of state. One new type of state is temporary contract storage, because right now there are different ways of storing data. There is the memory, transient storage, contract storage, which is persist forever. Then you have blobs, but blobs are not accessible via the EVM. So why not we create a new type of storage that is temporarily? So the main incentive for application developers to use this is very simple. It's going to be much cheaper to store things in the temporary contract storage compared to the permanent one. So that's the main incentive. And from the data that we know that most of the storage slots are used for a very short time. So if your application can store data in this form of storage, then it's going to be much better for your users as well. Concretely, how do we do this in protocol? In one of the EIPs, 8125, how we do it is that we use two system contracts. We auto-rotate it every 6 months, for example, to store the temporary contract storage, and then it gets cleared out every 6 months. So I don't want to go into the details, but you can check it out. But again, there are many variants that we can do. And last one. So this is one EIP that we proposed for the next fork, but we decided to put it off because we think that is kind of a distraction. It's not as important as other EIPs, but I personally think that it's important for the users because every time you deploy a contract, you pay the code deposit costs regardless of on whether the bytecode exists in the chain or not. And that's not fair for the users because, well, the bytecode is deduplicated internally in the execution clients. So the code that you deposit, if it already exists, there's actually no cost in terms of storage. So users shouldn't be paying this cost. So yeah, that's one thing that I'd like to see, at least in the future. And if you think this is important, I'll love to hear from you as well. And yeah, to close it off, I think this is just I would say this is just very early, and I would like to say that if the more that we can understand the state, the more that we can actually optimize it and make better protocol decisions. So yeah, thank you.
Thank you for presentation. It's end time for question.